All right, continuing deletion. So if there's no left subtree, we know how to do that. Otherwise, there is a left subtree. So I'm going to do something like, I don't know, L equals T arrow left. So L is pointing to the root of the left subtree. That's where all the action is going to take place now. Now the goal is to find the largest element in L and swap that up here to the root, bring it up to be the root of the tree. Because if we find the largest element in L and we remove it from L, everything in L is going to be smaller than that element. It was originally in the left subtree, so everything in the right subtree is bigger than that element, and L goes at the root right in the middle. So we preserve the search order, the traversal order. So how do we find the largest thing in this left subtree L? Well, we basically want to start moving to the right and come as far to the right as possible. So if there's a node over here and a node here, and there can be other nodes off to the left. But if we begin at the root of L and we just move to the right, so we can't move to the right any further, this is the biggest node in L. Okay, it's got to be, because if we go to the left, it's smaller, and we can't go to the right. And if there was something bigger, it would be to the right. So in general, we're going to start at the root of L, and we're going to travel down as far to the right as possible. So we'll break this into cases. So the first case here is there is no right subchild. So L has no right subtree. In that case only, this root is the largest node in the left subtree. So we want the root of L to become the root of the entire tree. So what we want to do here is make L the root of the entire tree. All right, how do we do this? Very simple. Say again?
I was just wondering, wouldn't you make L right equal to T?
Yes. So watch this closely. I want this to be the root of the tree. I want to get rid of T. I take this and I change it to this. That's all there is to it. So now L is going to be the root of the tree. The left subtree is exactly the same. The right child of L is what used to be the right child of the root. And T is going to go away. I'm going to free it. So do that once more. There's no right child on L, so just have that connect over here. All right, how do we do that in code? You already said it. But let's code this just based on this picture. Here's how things are right now. We're trying to change L's right child. And what do we want L's right child to point to? This node right here, which is T's right child. So that line right there does this. So it's not exactly like I showed you, because we didn't break that link from T to that node. We've got two things pointing to that node now. We don't need T anymore. That's the node we were deleting. So we can free that. And now this node is gone, and T is pointing to something that's been freed, so who knows. But the root of the new tree is just L. So we return L. And now this is the root of our tree. So that's deletion of the root when the left subtree has no immediate right child. So that's another case. The last case is when L right is not null. So this last case, there's a left subtree. I shouldn't have deleted that. L equals T left, and L right is not null. So we'll go back to our original, less funny looking tree. And we're going to hang some things off of here. Let me clean this up so I have some space. And all of this stuff that I'm drawing has no effect on our algorithm, other than the things coming off to the right. All right, what we want to do is move down from here until we get to the rightmost node. When we get to the rightmost node, we're going to change this to be the root, which means we need to change its parent to no longer point to this node. So we're in the same situation we were in when we deleted from a linked list. We need to look ahead one spot before we actually move. So I'm going to have a temporary pointer, which I'm going to start off right here. Let me get rid of this node because that's in my way too. We'll just add some nodes here. All right, so I'm going to start off with a temporary pointer, which is the root of the left subtree. And I'm not going to loop until temp right is null, because that's going to bring me all the way down to this node being temp, and I've lost track of the parent. So I'm actually going to loop while temp right is not null. Now I'm in a case where temp right, which is L right, is not null, so this is safe to check. Okay, it's not going to seg fault. So this is temp. This node is temp right. Temp right is the address of this node. Okay, well that's not null. I'm just going to move down the tree. Like that. So temp right is not null. I'm going to move temp to temp right, which is right here. Temp right is this node. That's not null. So I'm going to set temp to temp right and move down to here. Temp right is this node. That's not null. So I'm going to move temp to temp right, which will point me right here. But now temp right is null. So at this point, I'll exit the loop. And temp is the parent of the rightmost node. So here, temp is the parent of the rightmost node. All the other stuff in the tree doesn't matter. Right? We don't care how much complexity there is over here, because we know everything here is smaller than L, which is smaller than what we're looking at. And we don't care about the right subtree at all. All right, so temp arrow right is the largest node. That's the node that's going to become the root. All right, so we have to do three things. One, this has to become the root, which means we want this thing's left child to be L and this thing's right child to be whatever T's right child is. Two, we want to free the old root T, get rid of that. The third thing is we need to change temp's right child. Because right now, temp right is pointing to this node, and if this becomes the root of the tree, we've got a loop. And your traversal algorithms will now run forever until your stack blows up. All right, so let's do this in some steps. New root equals temp arrow right. So this is new root. Once I move new root to the root, what should temp point to on the right? Right, if I move this node up to the root, then temp should just be null on the right. But it's possible that new root has stuff to the left. And if I move new root up here, and I set temp to the right to be null, this stuff gets orphaned. So the trick is, we're going to let temp adopt on its right whatever is to the left of new root. If there's nothing to the left, we'll just let temp right become null. If there's stuff to the left, we'll let temp right become stuff. So we're going to have to say temp right equals new root left. And that'll cause temp to adopt all of this stuff or become null. And then we want new root to become the new root of the tree, so new root left equals T left, new root right equals T right. So now new root itself will point to this on the left and this on the right. That makes it the root of the tree. And then finally we free T. And that's your last case for deletion.
And ultimately, I guess I missed what we were trying to do with this.
This being what part of this whole 40-minute conversation. So this piece of it is deleting the root of a tree when there's a left subtree that has something to the right.
Got it.
But everything we've been doing other than those first three cases is deleting the root of a tree.
Okay.
Right, so first we did delete from an empty tree, nothing to do. If you delete from the left to the right subtree, you do those recursively, and all the rest of this would then delete the root. All right, so what do these steps do if we map them out? So we move temp down, we put new root right here. Temp right equals new root left. So now, temp doesn't point to new root, it points to new root's left child. New root left equals T left, new root right equals T right. So the effect is new root left goes here, and new root right goes here. And then we free T, so T goes away. And then we return new root, and so we tell the caller this is the root of the updated tree, which of course we can draw more neatly, just like this. There's your tree with the node deleted. This is really cool when you get it to work. It's really interesting when you don't have it working yet. You can get all kinds of Seg faults are the least of your worries. There's infinite loops, there's things pointing to themselves, there's things that are just isolated, they're just lost blocks. There's all kinds of things that can go wrong. But make yourself a clean picture, work with simple trees. Make sure your insert routine is working so that you understand exactly what tree you're working with, right? I recommend getting your breadth first search to work, because that's a really easy way to sort of get a picture of the tree. It doesn't show you the connections, but at least shows you the order of the nodes if you draw it right. Stick with small trees and write your code carefully and test each of these cases, right? These are increasingly complex cases. The most complex being you have a left subtree, you have something to the right, and the rightmost child has a left subchild, left subtree. But work up to it in cases. And be prepared, if necessary, to go into GDB and make pictures. Right, so you can look at a node, look at its data value, use different data values for your nodes in some meaningful way. And if you look at node arrow left, node arrow right, it'll give you a memory address. Right, so add that next to the node on the picture and build your picture from there. And it can take a while, and it takes, big workspaces to draw all this stuff out. This is good stuff to do with friends, good friends. Again, I don't want you, one person writes the code and somebody else types it in because they think they understand it. But for debugging, for looking at algorithms, things like that, definitely feel free to work with other people. Because helping somebody figure out what their code is doing or not doing will help you understand this stuff and get better at debugging it yourself. So delete's probably the last part that you'll write. Okay, or maybe free, or release. But it's cool when you get there. All right, yes?
So I just had a quick question. Like, if we have no left subtree and we're looking for the right, why wouldn't we look for the smallest thing?
You can do that too, but I'm making it a little easier on you.
Okay.
And you need to do it the way that we're describing, right? There's different ways to do this, there's better ways to do this, but if you do it a different way and I build a tree with your code and I delete, it's not going to look like it's working. And if I go through your code and you've got it well commented and I can figure out that you're doing something that's correct, you'll probably still get credit for it, most of the credit, but it's risky. So, and yeah, one easy way to pseudo balance is every time you delete, just alternate which side you delete from. Right? If you always delete from the left, you're just asking for a lopsided tree. Right? So it's not necessarily the way you would want to do it, but it simplifies the code. So other questions? This usually takes a while to sort of gel before you can even start writing code. But the insert and search and stuff like that is all good warm up for this. And by the time you get to delete, things like this, you've been writing this stuff enough that it will hopefully, you won't have to think really deeply about it to figure out what does temp arrow right mean, things like that. So start with insert, delete, comes later. All right, change of gears then. From binary search trees, which are about the simplest tree we can have, because if each node only has one child, we have a list. If each node has no children, we don't have anything, we just have integers or something. So having each node with 2 children is about the simplest tree we can imagine. The other end of the spectrum has something called a trie. And a trie is a really, really wide tree. It's a tree where each node has perhaps dozens of children.
Immediate children, or
Yes.
like not just left, right?
No, immediate children.
Oh.
And each of those children can have 20 or 30 or 50 children themselves. So you can store a lot of information in a trie without getting very deep. Right? If each node has 100 children, a single root node can store, well, it can store one piece of data, but the next level, you can have 100 nodes, and each of those can have 100 nodes, so you can have 10,000 nodes with only 2 levels to your tree.
But still no multiple parent per node, right?
But still only 1 parent per node, just lots of children. So this turns out to be useful for storing and retrieving large amounts of information quickly. So the example we're going to work with here is we're going to store words, which are strings composed of 26 characters, uppercase A through Z. No spaces, no punctuation, just uppercase letters. And here's what my root node is going to look like. It's going to be a node with 27 fields. So I'm going to think of this first pointer as corresponding to the letter A, B, C, D, Y, Z, and this last field is going to be an integer that I call EOW, for end of word. And originally, all of these are going to be null, and end of word is going to be a 0. So that's your state when you initialize a node. So a structure for this might be something like structure T node, and I'm going to have 26 pointers, which I'm going to call A, B, and so on up through C, Z, and then an integer, EOW, which marks end of word. And that's not how I would actually define the structure. I would actually make an array of pointers. But for simplicity, for drawing pictures on the board, I'm just going to assume my pointers are called A, B, C, D, up through Z. So I can label them like that. And EOW is just an integer flag. All right, here's what we do. Let's store the word cat into our data structure. So we come over to the pointer associated with C, and we check its value, and it's null. Everything I don't draw is null. So we create a new struct T node, and we take the C pointer and we point to this new node. And so this has those fields. All right, the second letter of cat is A. We look at the pointer corresponding to A, that's null. So we create a new T node and we point to it from this pointer. And down here, third letter of cat is T. We look at the pointer associated with T, that's also null. So we create a new struct T node, and we have that T pointer point to that. And here we set the end of word flag to a 1. All right, we've stored the word cat in our structure now. And we know that because if we look for the word cat, we look at the first letter as a C. We check this pointer, it's not null, so we follow that to a T node. The second letter is A. That pointer is also not null, so we follow that to a T node. The pointer for T is not null, so the third letter of the word that we're looking for is a T. We follow that to this T node, and here the end of word flag is set. that tells us that CAT is in our structure. All right, this is quirky. Let's keep going. Let's store cab, CAB. So we want to store a C, we come to our root node, we check C, it's not null. So we follow that down to another T node. Our second letter is A, we check the A pointer, that's not null. So we follow that to its node. We want to store a B, we check the B pointer, and that's null. So we create a new struct T node. We have the B pointer point to that. And we set the end of word flag to 1. So now we have 2 words in our try, cat and cab. Now if I search for the word CAL, what do? I start at the root, I look for the C pointer. It's not null, it takes me to a T node. I look for the second letter A. A is not null, it takes me to another pointer. I check the third letter C. I check the L pointer, that's null. Cal's not in my try. Let's store CA. So I want to store a C, I check the C pointer, it's not null. Takes me to a node. Second letter is A, I check the A pointer, that's not null. Takes me to a node. Set the end of word flag to 1. Now CA is stored in the try. So when you search for something, take each letter, follow your pointers. If you get to a pointer that's null, your word is not found. If you get to the end of your word and the thing it's pointing to is a node that does not have end of word set, your word is not found. So if I want to search for just the word C, I start at the root, here's a C, brings me to this node, check the end of word, it's not set, C is not stored. If I want to store C, I'm just going to flip this flag to a 1. That'll store a C. All right, let's store one more. Let's store cata. That's a Latin word for cat. So here's C, here's A, here's T, here's A. This is null, so I'm going to make a new T node. Going to have that A point to this new T node. And I'm going to set the end of word flag. And that's CATA. All right, moving on the basic algorithm. It's quirky, okay? It's weird because for one thing, these things are never actually stored anywhere. We don't have any letters stored anywhere in this. All we have is pointers and flags that are either 1 or 0. But from the way the pointers are set up, we can infer words that are stored or not stored in here. So it's a very indirect kind of data structure. It's very costly memory-wise. If you were to do a dictionary where you have lots of words that start with the same 5 or 6 letters, right, you're going to have a huge number of T nodes. Eventually, you're going to have a T node for every word that's stored in here. But it's, farming out geometrically based on how many different things start with the same words, same letters.
But if you're making like a, say like an autocorrect dictionary, predictive type dictionary where it's trying to see what word you might be trying to type.
Yeah.
It wants to limit down the dictionary.
Mm-hmm.
I'm trying to find a practical application for this.
So the practical application is that it's very efficient at storing words.
Okay.
if I want to search for a word, how many operations do I have to do to find the word in here?
As many as there are letters in the word?
As many as there are letters in the word. So if you're storing a dictionary of English words, and let's say your words are never longer than 20 letters, you never have to do more than 20 operations. Doesn't matter how many words you store. Guaranteed 20 operations, you can find your word or conclude it's not in there. And this end of word flag doesn't have to just be a Boolean 1 or a 0. It could be null for a 0, and if it's non-zero, it could be a pointer to some data structure associated with the word. So we could store the definition of that, right? And we could just malloc a string that holds a definition, and here we would store a pointer to that definition string. And now you can look up any word with however many operations there are letters in the word, which is kind of what we do with a dictionary, but with a lot more page flipping. So very, very efficient time-wise, very costly space-wise. But if you really want to do fast retrieval, it's hard to beat this.
So, whereas a hash table kind of simplifies down a word to a returnable index, this one assigns exactly one index directly related to how the word is spelled.
Yes, exactly.
So CAT is an index for that particular
Yes.
grammar location. Okay.
Yeah. And you find it by basically using each letter to find a pointer to the eventual thing that you're interested in. So you have to do n indirect references, where n is the number of letters. No collisions, right? So a theoretical hash is already retrieval time. But in practice, as you put more and more things in, you start getting collisions, your retrieval time starts to increase. Doesn't happen with a try. Right? We have a unique path. Deletion can be a problem, right? To delete a word, all we have to do is clear the end of word flag, but to reclaim that space is really tricky. Because once we've created this node, if we want to delete this word, we've got to decide if we still have other things that are being pointed to by it. Traversal is very easy. We can recursively traverse. How do you traverse? Just traverse the try pointed to by this, and this, and this, and this, and this, and this. To make it print nicely in traversal, you have to do a little bit of housekeeping. You need like a global prefix string. And when I'm traversing the try pointed to by this, I just set my prefix to C. And whatever I print in my traversal routine, I just prefix it with a C. When I'm traversing this, I'll change my prefix string to CA, and I'll put a CA in front of everything that I traverse down here. But it's still just a few lines of code. So traversal's pretty straightforward. Tries are really fun to play with.
Is try TRI or TRY?
TRIE.
TRI.
There's a reason. I don't remember what it is. But it's some kind of play on tree. So this is one of my favorite data structures. And it's another form of associative memory. All my favorites seem to be associative memories, hashes and tries.
I wonder if they use something like this when making those genealogy websites where you can go and explore like who's linked to who and all that kind of stuff. Or
Yeah, you can do that. Anytime that you have large numbers of potential next connections, a try starts to make more sense. Certainly you can store a collection of words in a binary tree, right? But the depth of that tree depends on how many things are stored. And here it really just depends on how many letters. So yeah, you can do this to store words, you can do this to store things besides words, right? So you could store numbers like this. You could have 10 pointers based on each digit, and you treat your number as a string, and you use the same kind of approach. And now you can store numbers with 50 digits in them. And the fact that your computer doesn't know how to deal with 50-digit integers isn't a problem, because you're just treating them as strings. And you can alphabetize strings, and it's just like sorting integers. So you can search through a catalog of, I don't know, whatever your favorite 50-digit social security number or something. And takes you a fixed number of operations. Alright, so tries are awesome. I've never assigned a try assignment, I might sometime.
Or again, the way the phone books used to work.
Yeah,
You'd have literally prefixes for whole states and then neighborhoods and cities. And
yeah, and you could locate someone partially by their phone number. You can do that with social security numbers too.
Yeah, that's always fun.
Yeah, the only random part is the last 4 digits that people give away for free anyway. All right, another change of gears. So this is weird because when Monday's a holiday or a snow day, we have like one class to cover like a whole week worth of material.
I've had like 6 or 7 classes so far this year. How many classes have we had this term?
So this is week 7, and we've lost at least 3 of our regular
We
scheduled
lost more than
days.
that. We've had 2 holidays and probably 3 snow days.
I don't think we lost 3 Monday, Wednesday snow days. I think we lost 1. We lost a Wednesday, and we had a Monday holiday week 2. I know it feels like that, though. So, change of gears again. Let's talk about heaps. So a heap is a different kind of data structure. It's not the same heap that we talk about when we talk about malloc. Right? Malloc allocates memory. We say that it's allocating from the heap. That apparently has no relationship to heaps as a data structure. Okay, so this is something different. So a heap is a way to store information in a data structure and retrieve it in a fixed order, either largest element first or smallest element first. It's not a structure we generally want to do searches on. It's not a structure we generally want to do deletions on. We just want to pull off, say, the largest or the smallest element from a set. So let's talk about a max heap. So we can add an element, and we can remove the largest element. And those are the main 2 things that we do with max heaps. Add something to the heap, and then, say, remove the largest element. One place you see max heaps used is in operating systems when you're creating priority queues to decide which job should get a bit of the CPU next. So each time a job requests the CPU, you throw it into a heap, and when the CPU is ready for a new job, you just say which job in the heap has the highest priority. You pull that one off, you give it a little bit of execution time, and when you're done with that, you go back to the heap and say, okay, now which job has the highest priority? So a priority queue. So we add elements, we remove the largest element. So what does a heap look like? It's kind of like a lazy tree. So this is like a binary tree. But it doesn't have that BST property where everything to the left is smaller and everything to the right is larger. It has a much simpler property. So the root is bigger than all children. That's the only property we need. So let's draw a heap. Let's draw a max heap. So 50, 40, 37, 36, 21, 38, 39. That's a valid heap. It's definitely not a binary search tree, right? We've got 40 and 37 on the wrong sides of each other, and we've got big things over here and a really small thing over here, but it satisfies the heap property, which is that the root is bigger than its children in all cases. Which means the root is bigger than all of its children's children, and so on. You can induct on the number of generations. And so the root of the entire tree is the largest number in that whole collection. Okay, therefore, max value is at the root. want to add things to the heap and we want to remove the largest thing from the heap. Those are our two operations. Let's talk about this first. How do we remove the largest element? It's just the root. So if this is your heap and you want the largest element, it's 50. And we get rid of that. All right, we don't have a heap anymore because we don't even have a tree because we don't have a root because we just deleted it. So we take the last element in the heap. The last element means go down to the deepest level and go as far to the right as possible. And a heap should always be filled in. Every level should be completely full before you move to a new level. And each level should be filled from left to right. So this is the last element. So let's write some code for this. So remove max. So return the root. Move last element to the root. Where the last element means bottom row, rightmost element. So this 21, this is going to become the root of the tree. But we probably still don't have a heap, because we just took something from deep down in the tree and we moved it up to the root. It's probably not satisfying the heap property. So now we need to do one more thing. We need to do what's called down heap. So what does down heap mean? Compare root with children if not bigger than both children. Swap with the largest child and down heap. So compare 21 to both its children. It's not bigger than both children. It's not a heap. We find the larger of the two children. That's 40. We swap the 21 and the 40. And we down heap from this point. Compare 21 to its two children, it's not bigger, so swap with the larger child, which is 39. So this becomes 39, 21, and down heap. It has no children, so it doesn't violate the heap property, so we're done. And we've got a heap again.
Kind of like a bubble sort gone backwards.
Yeah. But no iteration. At most, the number of operations we do to remove the max value is log of n. And because we're filling in this level before we go on to the next, for n nodes, the height of the tree really is log n. There's no notion of an unbalanced heap. And the most that we're going to have to down heap is 1 for each level, so it's order log n operations to remove the largest, which is pretty good. Yeah?
Could you repeat what the last two lines of number 3 are for me?
So compare the root with the children. If it's not bigger than both children, swap with the largest child and then down heap. So let's remove the largest node again. So we'll remove the 40. We'll replace it with the rightmost child, which is 36, the rightmost node in the root in the tree. And then we'll down heap. 36 is not bigger than both of these, so swap with the larger child, 39, 36, and repeat the down heap. 36 is not bigger than these, so swap with the largest child. This becomes 38 and 36. It has no children, it doesn't violate the heap property, we're done, and we've still got a heap. Next largest element, 39. Replace it with the rightmost entry, which is 21. and down heap. So this will swap with 38. And 21 and 36 are out of order, so that'll be 36 and 21. And we're done. And I made it a particularly nasty heap kind of by accident. So we're having to do a lot of down heaping every time that we remove something. But let's look at a different heap.
Does the left-right order matter too much?
Nope.
Okay.
Let's see. All right, so let's remove the 40 from here. So we pull off the 40, we're going to take the 34, put that up at the root. Violates the heap property, so swap it with a 39. So this becomes 39, this becomes 34, and now it satisfies the heap property. 34 is bigger than its children, so we're done. So in that case, our down heap only required one swapping of a node with its children. So sometimes you put the node at the top and it might end up being the root of the new tree. Sometimes you have to percolate down a little bit or maybe all the way to a leaf. But it's bounded by log n, right, the height of the tree.
What I add is basically just put it on the bottom right and see if it's bigger than the one above it.
So when you insert, you have to do the opposite. So insert, so add to, what did I call it over here? Add to right of last element, or start a new row if you're out of space, and then upheap. So what should we insert? Give me a number. 25?
Oh yeah, 25 is good.
All right, so we put a 25 right here and we upheap, which means look at its parents, see if it satisfies the heap property. 34 is bigger than both of these, it does, we're done. All right, let's insert another number, so let's insert 35. There's nothing more we can do to the right, so let's start a new row. There's 35. Look at its parent 10, does not satisfy the heap property. So we have to swap 10 with the larger of its children. So this becomes 10, this becomes 35. Now look at this node's parent. 30 does not satisfy the heap property. So swap with the larger of the children, which is 35. And now look at its parent. 39 does satisfy the heap property, we're done. Don't have to upheap any further, and we're left with heap. So inserting is also bounded by log n. So a million numbers, insert 20 operations, remove maximum 20 operations.
So just to make sure, it's not guaranteed that everything less than 35 is going to be under the 35 header.
Correct.
Okay.
Yeah, we've got 25 over here, for example. The only property it needs is that the root is bigger than both its children.
I'm trying to find why this is useful. I'm sure there's a good reason.
Order log n. Insert and order log n removal of the largest. The other thing is we can build a heap from a set of initial data very efficiently. efficiently than just inserting n times, which would be n log n.
But if you want to like retrieve the information stored in there, wouldn't that take, you'd have to go back and up and back and up?
The only thing we're doing is pulling off the largest element.
That's it?
Yeah,
Oh,
right,
okay.
this is the
Well, that's
structure when
easy.
you're only interested in pulling out the largest,
Okay.
right, or the smallest for a min heap. So something like priority queue, you just want to know what's the job with the highest priority. So you insert using this, and when you're ready to find the highest priority job, you just use the remove algorithm. And it
Oh.
efficiently gives you that number.
Cool.
Right? Terrible to search for a piece of data, because 25, we don't even know if it's to the left or the right of 39. Right? But for just finding the largest or the smallest, good to go. And these are really easy to implement without messing with pointers. Random tree. All right, here's a typical heap. Don't worry, these are just names for nodes, they're not actual data values. So this is a typical heap. Suppose we did something like PA1 and we tried to store this in an array. So let's make an array, call it heap. I'm not going to use element 0, but I'm going to store this in breadth first search order, starting at index 1. So I'm going to store A, B, C, D, E, F, G. When we upheap or we downheap, what kinds of things do we need to do? We need to identify our children, or we need to identify our parent. And we may need to swap a parent with one of its children. Right? So pick a node like B. Its index is 2. Its children have indexes 4 and 5. 4 is twice 2. Take a look at node C. Its index is 3. Its children have indexes 6 and 7. 6 is twice 3. So it turns out children, let me renumber these with their position in the array. So the children of node I are 2i and 2i plus 1. And the parent of node j is j over 2 calculated as an integer. So I've got a node stored here at index 6 and I want to know its parent. I know immediately 6 over 2 is 3. Its parent is node 3. If I have node 5, which was E right here, and I want to know its parent, 5 divided by 2 is 2.5. As an integer, that's 2. Its parent was B, which was right here. So we don't need to use pointers to build a trie if we have an allocated array. We can do index arithmetic and immediately find a node's parent or a node's children. So implementing this is really fun. It's just a little bit of manipulation on indexes to move around the structure. And this works because the trie is filled in from left to right, top to bottom. If we have gaps, this doesn't work, which is why we can't do this with a regular tree. But if we know the tree is completely filled in from top to bottom and the lowest row is filled from left to right, we have these two ways of finding parents and children if we store this in an array. So it's a pretty easy thing to code up. And we may do some programming assignments someday with it. We'll see. All right, so that's trees, that's tree deletion, that's tries, and that's heaps. Yeah.
So node I is 1 and node J is 2?
What does that mean?
Well, you said that, you've got node I, so children of node I, so what's node I?
So let me put these back. Suppose I start at the root, which is node 1, A, and I want to know what its two children are. Its two children will be 2 times 1 and 2 times 1 plus 1. They'll be stored in my array at index 2 and 3. Suppose I swap with node 2. So I swap entries 1 and 2, and now I want to find the children of node 2. It's going to be nodes stored at 4 and 5, D and E. So when I say compare a node to its children, right, if I'm currently looking at node 2, I compare it to the elements stored at index 4 and 5. Those are the two children of that node. Or if I say compare a node to its parent, if the node I'm looking at is 7, I know its parent is 3. 7 divided by 2 is 3.5. So I would compare this node with the node stored here. And if they're out of order, I would swap them. And then I'd look at 3's parent, which I knew was going to be 1. And if they're out of order, I would swap them. And 1's parent would be 1 over 2 is 0. There is none. I know I'm at the top of my heap. So instead of having struct node with pointers to the left and the right, we can just lay these out in an array. And if we want to find the child of a node, it's just twice that index and the position after that.
So labeling it node I and labeling it node J, those change. So those are going to be labels of a node that is going to change.
Yeah. It's just whatever node you're looking at. Yeah. So if you want to find the children of node 10, it's nodes 20 and 21.
Okay.
Yeah, it's just a placeholder. All right, so next week we're going to start dynamic programming. So dynamic programming is a way to speed up recursion in cases where a recursive solution is easy to write but really expensive to run. And we'll look at a few classic problems. One is called the knapsack problem, the other is a rod cutting problem. So knapsack problem, you have a bag that can hold a certain amount of weight, and you have an inventory of different items that weigh different amounts and they're worth different amounts. And the question is, which item should you put in your bag to get the maximum value? And you don't just find the most valuable item because maybe that's so heavy that you can only put one of those in. Maybe there's something worth a little less that weighs almost nothing, like diamonds, and you want to fill your bag up with diamonds. So how do you solve this problem in general? There's a really easy recursive solution, a relatively easy recursive solution, but it's really, really time intensive because it does a lot of recursion. So dynamic programming is a way that we can speed up these recursive solutions. So we'll spend next week talking about that. We'll go through a few classic examples, and probably your 5th programming assignment will be in dynamic programming. All right, so that'll be week 8. Week 9, we're going to talk about sorting. And we'll start with bubble sort, but we'll talk about insertion sort, selection sort, quick sort, merge sort, radix sort, a whole bunch of different sort methods. And we'll compare and contrast them, and we'll look at their order of complexity, which will probably take us into week 10. We'll talk more about order of complexity. We'll talk about some graph theoretic things, and we'll do a wrap-up of the course. And then we're out of here. So it's coming quickly.